Okay, here we go. So I looked through my slides for this, and I looked through Dr. Schmidl's slides for this, and his were nicer than mine. So we're going to use his, and we're not even going to change his name. They're all coming out of the same textbook, essentially. So here we go. This is chapter 1. And so the big concepts here are like a broad view of the immunity and the immune system. And I think the important thing here is that the immune system is actually a bunch of different, essentially independent cells that happen to be working toward a common goal but don't necessarily know that they're working toward a common goal. And so there are lots of ways that this could happen, but there's no central controller for the immune system. And it would be a lot more useful, I think, if there were, but that's just not what nature has given us. And so this is what we have to work with. The two big kinds of immunity are going to be innate immunity. And it's called innate because this is stuff that you can find even in a baby that was just born. These are the earliest kinds of cells. And the thing about innate immunity is that these cells and proteins and pathways react to kind of generic signs of danger, generic signs of infection or damage, something like that. They're not particularly smart. They're not tied into any one infection. There are lots of ways that they can be set off. Adaptive immunity, though, this is the kind that we really want. This is immunity against exactly the flu virus you had last year, something like that, or exactly against COVID-19, this particular strain that you've had. That's the immunity that you can carry with you, sometimes for years, and the innate immunity is always going to work more or less the same. The adaptive immunity is there to make it better and in some ways to shut off innate immunity because it's only useful to help really buy time for the adaptive immune system to work. So adaptive immunity is great. It's also created by a number of independent cells operating through just random processes. And so it takes a while. Usually in a person, it will eventually get to the right, result, whatever that happens to be. But it's going to try out every possible combination on the way there. And that takes a while, as you might imagine. And then the last bit is going to be, effector mechanisms of immunity, ways that these cells and molecules can come together to actually kill a bacterium or actually neutralize a virus. Since we're saying viruses aren't actually alive, you can't maybe kill them. Stuff like that. So let's go. Let's go. Okay, we'll start in early days of immunology because why not? Yeah. So the idea is that this is the study of the body's defense against all the bad stuff in the world. So immunology is behind your response to a virus. It's behind all the things you're feeling every time you get sick. It's also behind your immune response against pollen, which, if you're anything like me, is pretty severe. And these are all under the umbrella, if you like, of the immune system. And so, if I don't know, if we have to start putting people on, pedestals again and making statues of them, but if we had to make one for immunology, I guess it would be this guy. Edward Jenner made the first modern-ish vaccine. Although, if you were to actually look at what he did and compare that to modern clinical trial standards, the bar was a lot lower at the time, and you could get away with things that you cannot get away with now at all. So he took a gamble. It turned out to be right. I don't know that we should say, wow, he was a super genius for that, because a lot of people have ideas and take a shot, take a gamble, and a lot of times they're wrong. So, all right, yeah, good for him, but it's nothing necessarily super important. And also, so why not talk about eradication? So his discovery, Jenner's discovery, was a vaccine for smallpox virus. And we actually use a different vaccine now than the one that he originally came up with, we think. And yeah, with that vaccine and good public health measures, we were actually able to drive smallpox into eradication. It no longer exists in the world. The last person to catch smallpox in the wild, he got the very last case, was this guy, Ali Mal Malin, and he got it in Somalia, yeah, in 1977. It was the mild strain. He got over it. He was fine. There's pictures of him afterward. You get a couple of those little pock marks, like if you've had chicken pox, a couple of those. I know I have one right on my forehead. And other than that, yeah, seems to be okay. I have no idea what's happened to him since, but I wish him well. And that was the end of an era. So let's talk about immunity. Now it says immunity in vertebrate immunity. So this is animals that have bones like us. And it turns out that within that group, there's a specialized version of the immune system. You'll get something doing the job of an immune system in plants, in um, insects, in jellyfish, in mollusks, like an octopus or a clam. And they all kind of aim at the same goal, but the only ones that really have an immune system that's anything like ours are vertebrate animals. And within that group, it's really only mammals, so creatures that are pretty close to us that have fairly close relatives of our immune system. So the way our immune system works is this. You start out with a stem cell in the bone marrow, and this is called pluripotent because it has the potential, that's the potent part, to turn into many different kinds of stem cells. So that's the pluri part. It can turn into many things. And this thing actually turns into, eventually, all of the different cells. So it's going to make one of two things. It's going to make a myeloid or macrophage progenitor, or it's going to make a lymphoid progenitor. Lymphoid, these are going to be the things that we would call white blood cells. And so it's going to make dendritic cells, which are like little, they're kind of like little secret police, I'd say. They hide out in the tissues and they just wait, maybe even for your entire lifetime. They wait for some sign of danger to come along. And when it does, their job is to internalize it, pick up as much evidence as they can, and then go to basically the police station, which is like a lymph node, and report what they've found to all the other lymphoid cells. So they're part of the lymphoid white blood cell gang. Then you've got over here, you've got your B cells, you've got your T cells, you've got your NK cells. You've got a variety of cells. These each do different jobs. We're going to cover each of these things later. We're just doing a little quick overview now. We actually have a nice slide toward the end of this that we're going to look at, and I'm going to quiz you over on our next meeting on Monday. Over here on this side, so these are the guys that are going to turn into the adaptive immune system, the ones that can change their DNA to respond differently to different kinds of threats. And these can be activated and they can go into a memory state so you can keep them around for years, which normally doesn't happen, but they've got special powers, special privileges, if you like. Over here, you've got the dumb side. So this is the innate side of the immune system, and you've got things like, neutrophils. Eosinophils are heavily involved in allergy. Basophils are as well. These are full of histamine. And when you're taking an antihistamine, you are trying to tell the basophils and the eosinophils in particular to please just, calm down a little bit. Because this is allergy and we don't really need your services today. But thank you. And then a couple of these things, so these are the ones in the bloodstream, and then a few of them will then invade tissues. And so monocytes, when they invade tissues, will turn into macrophages. And a precursor of some sort. It's difficult to say because they all have the same DNA, and the only difference between these cells is which genes they happen to be expressing at the time. And so it's sometimes difficult to show exactly what cell becomes what other cell. But eventually we do make mast cells, which are like a tissue resident version of a basophil. They're basically a basophil that's going to live in your tissue. Then you got your platelets, which come from one great big cell. They're just little tiny bits that break off of the great big cell. And platelets are actually also involved in immunity. They are involved in an inflammatory response, which is our general kind of response to all sorts of danger and damage. And also coming from this same stem cell group are all your red blood cells. So this is, these hematopoietic pluripotent stem cells are actually responsible for most everything that's floating around in your blood. The stuff that we would call the immune system, which is really all these that are outlined either in blue or in yellow, and the stuff that we would consider more like just part of your blood, like the platelets and the red blood cells, or erythrocyte is the proper name for those. So here's the one. And I'm actually going to pause here. We'll come back and do a second part of this. But I would say you want to pause here as well and you want to have a look at this. This is a good starting spot, and this is what we are going. I'm going to see how well you know this at our next meeting. So this is just introducing the cast and crew of your immune system, of your 2000 and whatever year this is immune system. So yeah, take it in. Have a look at these guys. So let's give a little rundown. Neutrophils are great. So the big word that you see here, phagocytes. This means a cell whose job it is to eat other cells. It is an eating cell. Phage means eat in Greek, and cyte is, we use that word to mean cell. Let's see. So they go around eating things, and they have this wonderful thing. So I think of neutrophils as like just a guy named Phil who's just neutral, boring, just, glasses on the job, whatever. The thing about neutrophils is when they get activated, they go absolutely berserk. They will tear themselves open, literally killing themselves, and use their DNA. They'll sort of unfurl their own DNA, even though this kills the cell, like a net. And they call this the neutrophil extracellular trap, which actually is NET, so a net. And it's a net of their DNA plus some sticky proteins. And they're just trying to, destroy and engulf and trap any kind of bacteria or virus infected cell or potentially even cancer that can hurt you. These little guys love you, but you don't want to see them when they're angry because they go off. They go off. That's the way I remember this. Now, you can remember this any way that you like. Basically, the trick to this or any other class is coming up with, they call it a mnemonic, but it's basically some way to remember something. So I've got mine, but you should get some of yours, yeah. And if mine work for you, great. And but there'll be other things where I haven't made one yet. And let's see if we can put some together. Maybe we can do that. I don't know. Okay, then you got your basophils. I think them as basic cells of the immune system. They function in inflammation. They're full of histamine. They are floating around in the blood. They're just like a basic low-level immune cell. They don't do anything amazing. They don't do anything too terrible. They're they're average. They're basic, basically. They are just basic. Yeah. Mast cells are basophil-like cells that are actually resident in a tissue, and they do similar basophil-like things. The way I would remember mast cells is if you would get a mastectomy, you would have a lump of tissue from the breast removed. These are cells that actually live within tissues. So they're like a basophil that has invaded that cell. There's probably a better way to remember them, but I don't know. That's up to you. You let me know, because I want to know. Eosinophils are named after a dye called eosin that's bright pink and will stain these cells more than it stains other cells. So that's it. These guys are kind of left over from a different time. They're really good against some parasites and worms and fungus. And in modern day living, in houses with hospitals and stuff like that, we do not run into a lot of parasite infections the way primitive, ancestors used to. And so these are cells that don't have a lot to do. They're just kind of there, and they're saying, "Come on, throw me a parasite. Give me a tapeworm, so I can do something, so I can pound on it." And since we don't have these things, they're the ones that tend to go off in allergies. They are very much associated with allergies and really bad disease. They're essentially a part of the immune system that we've inherited. This is from an older time, but we kind of wish we could turn it off sometimes. Although there have been cases. I even know somebody who was kept alive primarily by her eosinophils. Yeah. When all the rest of her immune system had basically just collapsed, these guys were in there pounding on the fungus that was doing it. So, yeah, they have uses, but they tend to, yeah, I don't know. Idle hands or the devil's workshop, maybe. They don't have enough to do. They're underemployed. Over here, you've got your, let's see, your monocytes, which are the blood system version of a macrophage. It turns into a macrophage when it finds a sign of danger and then invades into the tissue, like spreads out and crawls in between the cells of the tissue, looking for wherever the trouble's coming from. So monocytes are floating around waiting for a signal. They're like, Batman sitting in his easy chair or whatever. And then macrophages are the bat. Yeah. Out, patrolling, trying to smash crime or whatever the heck Batman's supposed to do. I don't know. Then you got dendritic cells, which actually are more like yeah, they're over here on the kind of T cell side of things based on their origins. These are also little reporters. They're kind of like a macrophage in that they are waiting to eat something, digest it, and then go show it to some other part of the immune system. That's what macrophages do as well. But they are waiting in the tissues, so they're sort of lurking. They're, yeah, like sleeper cells, if you like, embedded in your muscles and your organs and just all around your body. You got these little dendritic cells that are camped out, and yeah, they're watching. They're keeping watch to make sure you're okay because they love you. All of these cells, yeah, would literally tear themselves apart to keep you alive, and I think that's kind of nice. Then you got the real actors, and so we're going to cover a lot about B and T cells in this class. T cells do a couple of different things. So you've got your killer T cells that actually kill regular cells of the body that are infected or in some way defective. They are, yeah, patrolling around and looking for danger and then destroying that cell. Because the cool thing is, the body can get by without pretty much any one cell. And so this is actually a really effective way to clean up problems like virus infection or bacterial infection. You just destroy the area. You just like basically nuke the area where the problem is happening, and then no more problem, and we'll regrow from stem cells. That's the idea. B cells are add an extra little layer to this. They make antibodies, and antibodies are really cool things that are shaped like the letter Y and that stick to pathogens. An antibody is kind of like a little, if you go to somebody's house and they give you those really fancy cheese cubes, you're not going to pick them up with your hands. What were you, born in a barn? There's going to be little toothpicks there. So you use the toothpick and stick it in there because we're all super fancy. An antibody is like that toothpick. It helps all the other cells of the immune system to pick up bacteria, viruses, broken down bits of stuff, and get rid of it. Destroy it so it's not laying around. So, yeah, B cells make antibodies. Antibodies help us clean up and help us mark targets for destruction, which is really neat. And there are several flavors of both of these things as well. There are natural killer cells, which are another version, kind of secret policey. Natural killer cells will roll around, and if there's a cell that's not showing whatever it's doing at that moment, cells have a way of showing what they're doing. It's called MHC, Major Histocompatibility Complex. And if a cell is not showing anything on those, or is just not showing any MHC, natural killer cells will roll up and they will destroy that cell pretty quick because something's wrong. A cell should always be showing a little bit of what it's making. That's how cells stay together. That's how the body can work. How all these independent cells can be in the same body and not turn into cancer or not turn into something else. Just, I don't know, something bad. It's kind of essential for life. It's like our life skill. All right, so that's where we'll pause this particular video, and then we'll go on with the next section of the video in the next one.